All right, so welcome back. Before we actually get started, let's start with a brief recap of what we discussed in the last class. So we discussed some important concepts in the last class, right? So again, just to put things in perspective, we are talking about the design of sequential circuits, circuits that can perform a sequence of operations autonomously, okay? And towards that, we need some kind of a timing mechanism incorporated into the circuits, and we are also missing the memory unit, right? Or we were missing until last week. We were missing the memory unit, and this is exactly what we have accomplished in the last class. We evolved from a simple latch, the SR latch, and we improved upon the device or the design, and we constructed what is called a D-flip-flop. Okay, and also in terms of introducing timing into our circuits, we talked about the use of clock as a signal that can be applied to the enable input of an SR latch, the improved version of the SR latch, or which is basically called the D flip-flop. So in the last class, we talked about the D flip-flop in more detail. Okay. Okay, that will be posted tonight. Okay, the homework 7 will be posted tonight. So D flip-flop, and so what is the D flip-flop? Again, that was derived from an SR flip-flop, right? Again, a flip-flop is nothing but a clocked latch. So if you clock an SR latch, that becomes a flip-flop, and we apply the clock at the enable input. Okay, all right. So D flip-flop, SR flip-flop, and what else did we do? So we realized that the D flip-flop that we derived was a level triggered flip-flop. So we discussed about the triggering mechanisms of the flip-flops. A level triggered flip-flop. What do I mean by triggered? My output, again, if you go back to the characteristic table of a D flip-flop, basically that looks like something like this, right? So basically you have D input and Q input. Okay, now I know that this particular flip-flop gets triggered on the high levels. We derived or we obtained a flip-flop that gets triggered on the high level. That means as long as the clock signal that is applied to the enable input of a D flip-flop is high, that's your enable input, that's your D, that's your Q prime. As long as the clock signal that is applied here is high, my output gets triggered by the input. That means my output sees the input. So we took the analogy of a wheel that has, in this particular example, that could be a semicircular wheel, something like this, right? Where that's your output, that's your input, and only when it's not blocked by this opaque object that is rotating. At what frequency? That's rotating at the frequency of a clock, for example. So it's rotating. Okay. Now, as long as this particular opaque thing is not blocking D and Q, my Q can see what is happening to D, and then Q can respond like D. So whatever changes are happening on D, Q sees them. On the other hand, once it's completely blocked, once it's completely blocked, you won't be able to see it, right? So I don't know how to draw this. So in this case, something like that, it's blocked. My Q cannot see D. So that basically corresponds to the memory state, right? And once the flip-flop is triggered, I can basically represent the characteristic table just by looking at D and Q. What I apply on D, my Q basically follows that. For a D flip-flop, if I apply a D input of 0, my Q basically becomes 0 on the next active level, right? If I apply a 1 on my D, on the next active level, my Q will also be a 1. So my Q follows D for a D flip-flop. Okay. All right. And it gets triggered for this particular flip-flop. This gets triggered on the high level. So that's basically that high level. That's your clock. This is your high level. So whatever is happening on D here at this level, my Q can see that. Okay. All right. And we also looked at some of the issues that can happen for a level triggered flip-flop. One important thing is we don't want to change the output more than once in a clock cycle, to make sure, because again the clock cycle is the one that is used to synchronize the activities of all the different modules that are connected, that make up your computing device, right? So that's used as a synchronization signal. You don't want anything to be anything to be operating, or anything to be outputting a signal that is higher than the clock frequency itself. Then the synchronization is gone, right? And oftentimes you design your system so that does not happen. Okay, if it does happen, in the case of noise, for example, that is basically occurring on a particular input, your input may change more than the clock period, or at a frequency larger than the clock period, which is basically indicative that basically corresponds to noise, and we want to filter that out. We want to reject that as soon as possible. Okay, so that's very important. And because a level lasts for a longer time, anything can happen on my D during this time, during this clock high period, right? We want to minimize that. So we came up with another device or another design of a flip-flop, in which case that basically responds to the edge, and we call that the edge triggered flip-flops. Again, the analogy here, if you notice this, this is a semicircle that which is representative of a level triggered flip-flop. So it's on half of the time, off of the time, right? So semicircle, it's rotating, it's on, that means it's not blocking D and Q half of the time, and it's off half of the time. On the other hand, if I have instead a wheel that is something like that is still rotating but only a slit open, this is exactly what the analogy that we have taken last time, just a very narrow slit open, and it's rotating. Okay, so most of the time my Q does not see D. It only sees D when the slit is aligned between D and Q, right? Only then I can actually see through that slit, and that slit lasts for a very short time. That's exactly what we talk in terms of the edge triggering mechanism, edge triggering. So here are my edge. My edge lasts for a very short period. So what is happening on the edge? For example, if I design a flip-flop that is a positive edge triggered flip-flop, these are my positive edges. So whatever happens here, at this instant, my Q gets triggered, and it does not get triggered until the next active edge, which is this edge, right? And I only have one edge in a clock cycle, one active edge in a clock cycle. If I design a flip-flop that is positive edge triggered flip-flop, I only have one positive edge within a clock cycle, right? So that ensures that my output only changes once per clock cycle. Okay, so even if my D changes during this time, my Q does not get affected by that. It can only change once per clock cycle. So that constrains my Q to change only once per clock cycle. So that's your edge triggering. How did we derive that circuit? So basically we looked at the master-slave configuration. The master-slave configuration where one D flip-flop drives the other D flip-flop, and the clocks are inverted. The clock from the master is inverted and applied as a clock to the slave flip-flop, and that gives us the master-slave configuration. And we observed the behavior of that through the aid of a timing diagram in the last class. Okay, and we saw that the output of the slave flip-flop basically functions as a negative edge triggered flip-flop, right? Similar to a negative edge triggered flip-flop. So that's how we derived a circuit that can actually give us an edge triggering mechanism. And that in the last example, we basically looked at a circuit that was a negative edge triggered flip-flop. Now, what else did we do? So, when D flip-flop, again, as the name suggests, D stands for data, so it can be used to store data. And in the last class, we looked at one example, one possible example of utilizing a D flip-flop to construct a register. And it's pretty simple, right? A register or a data register that can store data, and this can be constructed within a microprocessor, okay, or a CPU of a microprocessor, okay. And these data registers can hold temporary. Again, you don't have a large number of these compared to how many memory locations you have in a memory, external memory. Okay, but these are again used for high-speed operations, basically used to store temporary data while you're manipulating the data, while you're working with data, while you're working with computation of data. Okay, so you basically store that data from the memory onto your local registers, and then work within the ALU, within the CPU, among those data, and then once you perform the computation, you put back the result back in the memory. Okay, so that's how the operations work in an actual microprocessor. That's how you program a microprocessor. Okay, so that's your data register. We talked about how to construct one. Again, the good thing about the way we do things in digital logic is if I can do for 1 bit, I can basically extrapolate that to n bits just by simply copy and pasting those multiple units. And this is exactly what we've done in the last class. So I can construct a n bit register by copying and pasting these multiple D flip-flops together. Okay, so that let's say I have n bit register by having n D flip-flops like this. Okay, and in this case, we took the example of a parallel load operation. A parallel load where each of the flip-flop is connected to the data bus, and when the load enable is enabled, I store the data from the data bus comes and gets stored on my register instantaneously, all at once, right? So that's called a parallel load. We are loading all of the data into each of my D flip-flops, constituting this n-bit register in a parallel step. That's why it's called a parallel load operation. And we also examined how to, again, in a typical CPU, you have multiple registers. You don't have a single register, right? You have multiple registers, and each of the register is connected to the data bus. So let's say you are working with n-bit data. That means your data bus consists of n lines. Each line is connected to one of the flip-flop of the register. Okay. So now one of you in the last class asked about, okay, because the D flip-flop basically follows my Q input, or the Q output of a D flip-flop follows the D input. Okay, how do I make sure that when data is changed on the data bus, I'm still storing the data in my D flip-flop without being overwritten with new data that is placed on the data bus? Okay. And to account for that, we looked at how it is actually done. So basically, you have for each of my flip-flop, you also have a 2-to-1 multiplexer, which is configured in this way. So we talked about this approach, right? So you have I0, I1. You're basically feeding back the output back to the input of the D flip-flop, and then one of the other input of the multiplexer is connected to the data bus. That way, once this multiplexer is enabled, let me call that the load enable signal is applied here. If I want to address this particular register, then I place a load enable signal as 1, in which case I'm loading the data from the data bus into my D flip-flop on the next active edge, or on the next triggering instance. Okay, and if I want to keep that in memory, all I have to do is I place a value of 0 on my load enable. Yeah, Johnny, you have a question? Okay. All right. So this is what we discussed in the last class. So if we put load enable as 0 here, then I'm basically putting that in the memory because I'm feeding back my Q back to D, and then once on the next triggering instance, Q follows D. And so basically nothing is changing on my Q. Okay, so that's the idea behind the setup. Okay. Now load enable. Okay, that's a load enable. EN is not clock. This is a load enable. Okay. That's the enable signal here where you apply the clock. Okay. So this is the setup we examined in the last class. All right. So now with that, now let's move on. Now let's look at just extending the discussion that we had in the last class, right? Where we have multiple registers. Let's say this is my A register. Configure this as A. Let me call this B, C, and D. Let's say each of these are 4-bit registers to start with, just to make sure that we make the things simple. So each of my register can hold 4 bits of information. I have 4 of these registers in my CPU, and I want to address them. And again, I have this common data bus, right? 4 lines that are connected to each of my registers, something like this. Again, when I show this, that means you need to imagine, or you need to assume that we have this entire module of having the multiplexer and the D-flip-flop together within each of this block. Okay, so that's my registers. That goes here, that goes there, that goes here. Likewise, each of my register is connected to the data bus. Now, while I'm programming this particular device, I need to basically address this. I need to send an address in my code to make sure that I'm choosing the right register. So how do I do the addressing? So let's try to answer that here. How do we build an addressing scheme, a simple addressing scheme that and let's say these are my DE, A, DB, DC, DT. That's your load enable signal. Let's say that's your load enable, and each of my flip-flops or each of my registers are connected to the master clock. So each of them are synchronized with the master clock. So that's your master clock. That's your enable inputs for the flip-flops connected to the master clock. Okay, and that's your load enable input. Load enable input. Again, although I'm showing it to 1, you can imagine that each of these have similar load enable inputs. All of them are connected together for one particular register. Load enable input. Load enable. Load enable. Okay, so I have 4 registers, and I want to come up with unique addresses for each register. So how many, again, if I want to come up with a unique addressing mode, I need to again use binary bits to form the address, right? So how many binary bits should I use to form a unique address for each of my register? Basically, it's a simple question, right? I have 4 registers. How many binary bits I need to use to come up with a unique code? 2 binary bits, right? So for example, if I want to address this particular register, let's say the address for that is 00. The address for A is 00, for B is 01, for C is 10, for D is 11. Okay, and let's say on the hardware, A and B correspond to the bits that carry the address. That means when I'm writing the code, okay, if I want to store the data on B, for example, that means I would assign AB to a value of 0, 1. In which case, only this particular load enable signal should be activated, right? So that's for A. Let me put XY just to distinguish between them. So those are the bits that carry the address. I should be placing 1, 0 on this. Yeah. 0, 0, 0, 1, 1, 0 on this, 1, 1 on this to make them active. Okay. All right. So I have A, B, C, D. If I want to make this active, I would place XY as what? The address for that was 0, 0, 0, 1, 1, 0. So I would place XY to be 1, 0, and only this particular line should be active. So that I can basically store, I'm telling this register, okay, now I would like you to load the information from the data bus on this particular register. Okay. So how do we build this addressing mode? How can we build it? If you notice this, what it means is if I place 1, 0 on my X and Y values, so I'm building a circuit something like this that takes in X and Y values and produces X prime, Y prime, X prime, Y, XY prime, XY values, right? In other words, it's taking these values and basically giving out the min terms corresponding to those two input values, right? So these are nothing but the min terms. But if I have 2 bits, I have 4 min terms corresponding to that, right? 2 input bits, I have 4 min terms. Okay, and this particular circuit, it has a special name. It is basically called a 2 to 4 decoder. A decoder can be very helpful for these applications. So basically, I have 2 lines to 4 line decoder, right? So I'm taking a code, and then based on this code, I'm only making 1 line to be active at a given point, right? Based on this code, just like a min term, which is unique for a particular given input, right? And only 1 min term is active at a given time, exactly the same way. All right. So basically that circuit should be pretty simple to construct now. 2 to 4 decoder. So X and Y. So those are my inputs. That will be X prime, Y prime, and I will connect this to 0, 0. So in which case, if I place 0, 0 on my XY, okay, only this one will be active, right? This one will be 1. I'm placing a load enable signal as 1. So that means I'm telling I'm trying to copy the data on the data bus onto my A register. Okay. Likewise, this will be X prime Y, X prime Y, connected to B, XY prime, connected to C, and then XY, connected to D. So now I have the addressing mechanism as well. So now based on what I apply on XY, I can pick and choose the register, right? I place 1, 0 here. All of these lines are 0 except this particular line. So I'm basically picking and choosing C register to store my data. And likewise, okay? So I can pick and choose different registers based on the address I provide on X and Y values. Okay. All right. And of course, I have to synchronize all of the actions with respect to the master clock. That means when do I place the data on my data bus? I need to synchronize with the master clock on it. So basically, I need to place the data on an inactive level or edge. Okay. Apply the right address. and on the next active edge, the data gets transported to my register, and then I would basically take out this place a different value on my x and y. So every activity is basically synchronized with the master clock that way. Okay, so let me take a pause here and let me see if that makes sense. And again, this particular circuit is a 2 to 4 decoder. I can have multiple sizes of decoders. That's a 2 to 4 decoder. If I'm working with 3 lines, 3 input lines, that means I'm working with a 2, 3 to 8 decoder, and so on. So the size of the decoder basically changes that way. Okay. You can also think about decoders as the demultiplexers, as a complementary as a device that performs in a complementary fashion to a multiplexer. Okay. All right. So, and again, these decoders are also a class of belongs to the medium scale integrated circuit family, just like your multiplexers. So that's another example of utilizing a medium scale integrated circuit in your design. Okay, with that, let me take a pause and see if you have any questions so far. Does that make conceptual sense? Are there any questions here? I just wanted to give you a intuitive understanding about how different things are connected inside your computing device. How you can address a particular register, for example. And you have similar schemes for addressing memory, where you have these memory cells, and then you have each memory location would have a particular address, and you have the write, read operations. How would you write information into your memory? How would you read from a memory? How would you basically address a particular memory location, and so on. If you have time during the later weeks, we can also think about covering that as well. Any questions so far? How are you guys feeling so far? All good? There are no questions. Let's move forward. So these are some of the applications. So I'm looking at some of the applications of flip-flops. Okay. So we looked at the D flip-flop. Now, just like how data can be loaded parallel. So we just looked at the example of a parallel load operation, where my data lines are connected, or each individual data line is connected to one flip-flop. And once the load enable signal is enabled, then all the data comes in a single clock pulse. All the data comes and gets stored in this register. So n data lines are connected to n flip-flops. Then n bit data is stored in a single clock pulse. That's why we call that a parallel load operation. Okay. Now we also have, and oftentimes you also work with sequential operations, or serial operations. And we do that every day, right? When you're trying to stream some information, right? You're doing a serial operation. You're not getting the entire data in a single instance, right? In a single download step. You're basically streaming information. When you're watching a live event, for example, you're streaming information. For example, what you're watching right now is being streamed to you, right? So one bit at a time goes into your system, okay? Because it happens at such a fast rate, you won't see the lag most of the time, or you won't really feel the lag, but the lag is there. Okay. Now, for serial operations, and we'll talk a lot about the serial operations later on when we design other circuits. For serial operations, what you're really doing is you're working with data one bit at a time. One bit at a time. What that means is, now how are you synchronizing this? You're receiving one bit, and at what rate are you receiving it? And again, that is determined by the clock. Because your clock is the timing signal here. Everything works according to the clock, with respect to the clock, right? So I'm getting one bit at a time, with each clock pulse, with each active edge of the clock pulse, or active or with each triggering instance of the clock pulse. Okay, so that's synchronized with the master clock. Now, for serial operations, it's very essential that you work you have or you work with serial registers or shift registers, also called shift registers. So these are slightly different from what we have just seen. These are shift registers, but very simple in construction. There is nothing majorly different here. We are still going to use the data, the D flip-flops, to construct them. The only difference here is the way I would connect them together. Previously, each of the input of the D flip-flop was independently connected to the data bus. In this case, that's not the case. So you have this so let's say if I'm trying to build a shift right, because when I'm trying to shift data, I can shift right or shift left, right? So let's take the example of a shift right register. So in this case, I have, let's say, a 4-bit register I'm trying to construct. I have 4 flip-flops, and that's my serial input. So I would connect my D, let's say this is my DA, to the serial input line, serial input line. Again, each of my flip-flop is connected to the master clock, because my master clock is the one that synchronizes all the operations of all the different elements, the timing operations. So I need to make sure that this is the one that determines the timing for each of the clock. So that's my clock. Let me see, that's DB, DC, and DD. Now, the way I would connect, I would drive DB register flip-flop by using the output of the DA flip-flop. The QA drives DB, QB drives DC, QC drives DD, QD. So now I have basically a simple shift right register. Okay. Now, and how does it work? So basically, let's say this is my serial input coming in. 1 bit at a time. So I'm synchronizing this serial input with respect to the clock. So 1 bit at a time comes in. Okay. So on the first clock pulse, let's say everything is cleared to be 0 in my flip-flop. So that's my D, that's my QA, QB, QC, and QD. Okay. So so let's say this is my data coming in. That is my serial data. Okay. Now on the first clock pulse, so let's say that's the clock pulse. That's the 0th clock pulse. On the first clock pulse, I'm already applied is 1 here. On the first clock pulse, on the first triggering instance, if you will, my QA gets triggered. So my QA gets the value of 1. The output of this is applied as an input to this flip-flop. Again, before it was 0. So that basically gets pushed onto QB. QB value gets pushed onto QC. QC gets pushed onto QD. So I'm shifting the data. Right? On the second clock pulse, my 0 gets pushed onto QA. 1 gets pushed onto QB. Again, 0 from QB onto QC, 0 from QC onto QD. On the third, this 1 gets pushed onto QA, 0 to QB, 1 to QC, 0 to QD. So now I have stored 1, 0, 1, and then on the fourth clock pulse, I have again another 1 gets pushed onto QA, 1 gets pushed onto QB, 0, 1. So it takes me 4 clock pulses, as you can see, 4 clock pulses to push a 4-bit information serially into my shift right register. So that's my shift register. That's how I would construct a shift register, shift right register. And likewise, you can also construct a shift left register where my data is being pushed from the left side to the right side. Okay. So now we have looked at operations like a register, a parallel load register where I can load information. Okay. Now, what do I mean by reading information? Basically, reading basically implies I'm just getting these values and taking note of these values. That's how I'm reading the values. So I can read the values in a single step parallelly. I can wait 4 clock cycles until the data is stored, until the 4-bit information is stored in my 4-bit shift register. And then on the 4th clock pulse, I can basically come and read this data in a single step, or I can read the data serially as well, right? I can read the data here. So as my clock pulses are being advanced, right? After the 4th clock pulse, starting with the 5th clock pulse, I can start reading the data from my initial serial information. So you can read it parallelly, you can read it serially, right? You can, and we also looked at the example of a parallel register where you can load information parallelly and read information parallelly as well in a single clock pulse. Okay. Now we can also construct registers that are so-called the universal shift registers. Okay. Let's see what the universal shift register is, and then we'll talk about what are the applications of these. How do we construct one? A universal shift register. As the name suggests, a universal shift register is one that can perform both parallel operations as well as serial operations. So that's basically constitutes a universal shift register. Okay. So when I say parallel and serial operations, this is what this can actually do. So you can do shift right, shift left, parallel load, or memory. We can just do memory here. It can be used to store information. That means you don't want to do anything. Once I've stored something, I want to store them. And with each passing clock pulse, I don't want to change the data. That constitutes a memory condition. Or I can shift right my data as with each clock pulse. I can shift the data right in my register. Or I can do shift left operation, or I can do a parallel load operation from the data bus that we have already seen. So a register that can perform all of those operations is called a universal shift register. Okay, let's see if I can construct one, and I would like to see if you can provide some suggestions or ideas on how to construct one. I want to construct a hardware circuit that can be configured to do these multiple things. So what is the first thing that I should be thinking about having in my circuit? What is the design rules that we came up with? When we want to have a single piece of hardware, we want to make this multifunctional. What is the critical thing needed here? Any suggestions from the class? Anthony, do you have any suggestions on this? Yes, absolutely right. We need a control. We need a control input that would tell the hardware how it should be configured at a given instant of time. Right? Now, how many control inputs should I have here? David? Yes, two. I need two control inputs. Two control inputs. That's perfect. I need two control inputs because I have four different operations, right? Either I have to configure it as memory, as a shift right, shift left, parallel load. So let's say control input is xy. Okay. So I can now say, okay, when I put a value of 0, 0 on my xy, then that corresponds to, I would design my hardware so that corresponds to the memory operation. Placing 0, 1 on xy, that corresponds to shift right operation. 1, 0 on my xy corresponds to shift left, and 1, 1 corresponds to parallel load operation, where I want to store the data from the data bus parallelly onto my shift register. That's a parallel load operation. Okay. All right. How should we construct it? What should I use here to construct one? Again, going back to our design of the of a simple parallel load register where we use a multiplexer, right? So your multiplexers can come really handy here. That's another example of how we can apply multiplexers in our design. So that's a mux. So we will use a mux in the design of this particular circuit. Okay. So when I'm trying to use a mux, I will apply these, my x and y, on the selector inputs of a 4 to 1 mux. So I will apply these values on the selector inputs of a 4 to 1 multiplexer. Okay. All right. So now let's look at the design. It's actually, once you know the operation of a multiplexer, you know, which you already know, it should be pretty straightforward, hopefully. Okay. So let's see if you can follow me through. Yeah. All right. So let's say these are my, again, because that's a register, I have to use a D flip-flop in the design. So let me use a D flip-flop in this design. Okay. So that's my, let's, in this particular example, let's actually design a 4-bit universal shift register. So I'll use 4 of these that can store 4 bits of information. Okay. And we call this DA, QA, DB, QB, DC, QC, DD, QD. And these are the enable inputs for this flip-flop, which are connected to the clock. All of them are connected to the master clock. So everything is synchronized with the master clock. And that's your clock. Okay. All right. And I will use my multiplexers now in this way. Okay. That's the output of the multiplexer. Those are the inputs, I0, I1, I2, I3. That's it. Again, that's a 4 to 1 multiplexer. I'll use 4 of these. That's the output. I0, I1, I2, I3. I0, I1, I2, I3, and one more. This one is going to be tricky. Okay. All right. And these are the selector inputs S1, S0 for the multiplexer, where I'm applying my X and Y. Although I do not show these, each of my selector inputs are tied together. Okay. That means on each of my selector inputs, I'm applying the same values of X and Y. That's going to be X, Y, X, Y, X, and Y. That's the output. Okay. All right. So first, let me do this. Let me apply the output of the multiplexer, just like what we have done in the design of the parallel adder. Okay. I'm applying the output of the multiplexer, each of the output of the multiplexer, to the input of the corresponding D flip-flop. Something like that. Okay. All right. Now again, if you remember, with 0, 0, I wanted to get the memory operation. 0, 1, we wanted to get the shift right operation. 1, 0, shift left operation. And 1, 1, what was that? Parallel load operation. Okay. Now when I apply 0, 0 on my multiplexer inputs here, what is being routed to the output? For this particular multiplexer, when I say again X, Y, 0, 0, that means I'm applying 0, 0 on each of my multiplexers. When I'm applying a 0, 0, that means I0 is being routed to the output, right? Now I want to configure this as memory when I apply 0, 0. That means any new information should not be overwriting the values that are already stored on Q0s, or QA, QB, QC, and QT in this case. And one way of ensuring that that does not happen is by feeding back I0s, just like what we've done for the parallel load operation or parallel register. We've already done this. I'll just do this. Okay. Now when I apply 0, 0, all I'm doing is feeding back my Q back to DA. So with every progressing clock pulse, I'm not changing the value of QA because the same value is being fed back over and over again. I'm not changing the value of QA. So that satisfies the memory condition, right? Now what about shift right? I want to perform a shift right operation when I apply a value of 0, 1 in this case, over here. If I apply 0, 1, I want to make sure that the contents of this register are shifted to this, the contents of this register are shifted to this, the content of this flip-flop are shifted to this flip-flop. How do I ensure that? In what way should I connect so that happens here? Do you see any connections, or do you see any anything here in the circuit that I should be doing to ensure that when I apply a 0, 1 on my multiplexer here, I get that shift right operation? Any ideas here? The content of QA is in I0. Content of QB is the same as I0 in this case, this I0. QC, QT, yes. So if I want to shift right, okay, that means when I say 0, 1, that means I1 is being routed to the output, right? In this case, I1 is being routed to the output here, which is being connected to DA. I1 is being routed to the output, which is connected to DB, and so on, right? So if I want to obtain a shift right operation, what should I be doing? This is what I should be doing. So that's your serial data coming from the right. That means when I apply 0, 1, I1 is being routed to the output. That means I'm connecting my DA to the serial input here. So with each clock pulse, I'm taking one bit at a time from the serial input, and then it's basically being routed to the QA. Now, if I want to shift the data from here to here, the output is again contained in I0. This is the same line. So basically, I need to connect this to I1 of the next flip-flop. That ensures that in the next clock pulse, I'm shifting the value of this into this flip-flop, right? Because I0 is being applied as an input to I1. I1, and when I place 0, 1 here, I1 is being routed to the output, and my flip-flop basically follows the input. So I'm shifting the value of this flip-flop to this flip-flop. Likewise, if I want to shift the value of this flip-flop into this flip-flop, I will connect the I0, which is basically the node value of that flip-flop, to I1 of this flip-flop. And likewise, there you go. Now I got the shift right operation. Does that make sense, guys? 0, 0 corresponds to the memory, so we have the feedback. 0, 1 corresponds to the shift right, so I'm shifting the I1, shifting the I0 value here into this, and so on. Now, what about shift left? How do I get the shift left operation? When I apply 1, 0, right? When I apply a value of 1, 0 on my x and y, I need to obtain the shift left operation. And let me see if you can help me with this now. How would I connect? Based on what you've already seen, how do I connect to get the shift left operation now? Any suggestions? James? Do you have any? How about Fabian? Use I2. Okay, very good. That's a good suggestion. Obviously, because when I say when I say 1, 0 applied on xy, my I2 is the one routed to the output, which is being connected. So that means whatever I connect to I2 is being connected to DA, to the D inputs of the flip-flops, right? Okay, so how should I do this? Use I2, that's fine. In this case, I need to shift left. So that means the contents of this register needs to be shifted to this. The contents of this register needs to be shifted to this. Contents of this to be shifted to this. When I say content, that means QD value of this flip-flop should be shifted to QC. QC value to be QB. QB to QA. Okay, so my shift left data, or the serial input data, should be applied here. That's the serial input. Left. Try to. Okay. And then, what about this one? Where should this be applied to? I want to shift this content to this register. And this content is basically connected to I0. Right? So that means my I2 of this should be connected to I0. Okay. Like that. Okay. Now this content has to be shifted onto this flip-flop. That means the I0 of this should be connected to I2. And likewise, this should be shifted here. That means the I0 of this should be connected to I2 of this one. So now I have a shift left operation. So that is also done. And finally, the parallel load. So when I apply a 1 1 on my x and y values, then I will be basically obtaining the information from the data bus, and in the next clock pulse all the information should be uploaded onto my register in a single clock pulse. For 1 1 condition, again I3 is the one that is being routed to the output. That means because I want this particular condition to be parallel load, so that should be basically coming from the data bus. Let me call that D0 or D3 or D3 line of the data bus. This should be D2 line of the data bus. This should be D1 line of the data bus, and this should be D0 line of the data bus. Okay. And now I have a universal shift register, a register that can perform all of those operations. And of course, reading does not, I don't have to worry about reading because I can do the reading in a single pulse. I can do the reading as a serial data, like we just discussed. Right? Okay, so that's the universal shift register. That's how you would construct a universal shift register. And you can see the importance of multiplexers in the design. How you can use multiplexers to add multifunctionality to your device, to your design. Okay. All right. So let me take a pause here. I want you to observe this and let me see if you have any questions on this. Okay, so if none, then let's move on. So that's your, again, we're looking at the applications of flip-flops. Looked at the serial register, we looked at the parallel register, we also looked at the universal shift register, how we can construct a universal shift register from a flip-flop. And again, the important thing is all the timing is controlled by the clock. Everything is synchronized with the master clock, as you can see in this example. Okay, so now I'm able to introduce the timing information into my design, at least at this time still in a primitive sense, but as we will see later on, we can see how flip-flop really helps the device to progress in time. Okay. All right, so that's good. Let's look at some other examples of flip-flops. Okay, that was your the universal shift register. Now let's get back to the triggering ones, the triggering mechanism. That's a very important concept, and that's something that you should really get. All right. Now we looked at let's look at the symbolic representations first. So this representation of a flip-flop, where you're applying the clock here, this corresponds to the level triggered flip-flop. That corresponds to a level triggered flip-flop. Okay. A flip-flop that is represented this way with an edge, something like that. Where you're applying the clock, again, that's your enable input. This corresponds to a positive edge triggered flip-flop. This is a positive edge triggered flip-flop. That means this particular flip-flop responds to positive edges. These are my positive edges. My Q follows D at these points, at these edges. So those are my triggering instances. So that's a positive edge triggered flip-flop. We also have negative edge triggered flip-flop, which we derived last time. That's your negative edge. That is represented symbolically with a bubble. Yeah. The edge symbol and the bubble symbol represents that this is a negative edge triggered flip-flop. In this case, this flip-flop is getting triggered on the negative edges or the falling edges. We can call it positive edge or rising edge. In this case, that's a negative edge triggered flip-flop. Or falling edge triggered flip-flop. Both are synonymous. Okay. So these are the different types, and from now on, unless otherwise specified, we'll be working with edge triggered flip-flops for obvious reasons, right? We have already discussed what are the reasons why we should be going for an edge triggered flip-flop in the first place. Triggering happens only once per clock cycle, okay, on a single edge. Okay, now let's examine this circuit, again built from the D flip-flop. Now again, for an edge triggered flip-flop, we can describe the characteristic table this way. Characteristic table. Okay, that's your D input, D of T, let's say, Q of T plus 1. When I say T plus 1, that corresponds to the next triggering instance. What happens to Q on the next triggering instance? I'm applying some value on D. Okay. Now my Q does not respond to D unless the triggering instance has occurred, right? So on the next triggering instance, how does my value of Q change? That's what it means. So when I apply a value of 0 on D of T in the present time, then on the next triggering instance, if I wait one triggering instance, then the value of Q of T plus 1 is also 0. If it's 1, the next triggering instance, the value is 1. Okay, so I can write the characteristic table now when I'm talking about the edge triggering mechanisms. When I use this representation that corresponds to what is happening to Q on the next triggering instance. Okay, these are my rising edges. So for example, if I apply a value of Q here, nothing happens on Q. If I apply value of D here, nothing happens to Q until the next triggering instance happens here. My Q value gets triggered at this instance. That's your QT plus 1. That's what it means. Okay, so now let's examine this simple circuit that is derived from your D flip-flop. Okay, I just modify that a little bit with some combinational logic, and I obtain this and see what purpose it serves. Okay, so I have this D flip-flop. I take a single D flip-flop. This is an edge triggered flip-flop. Let's say this is a negative edge triggered flip-flop. That's where you apply the clock. That's your Q and Q prime. Two outputs available to you for use. So I'm just adding some circuit here. Okay, so what I will do is I'll do this modification. I'm just adding this part, combinational circuit part, to my D flip-flop. Okay. And I will take Q prime. I'll say that this is my J input. And call this K. These are some inputs. I'm designating these as some inputs. And I take this feedback again. Take Q, apply as one of the input to this AND gate, and have this. Now I want to analyze this circuit. What kind of a purpose does this circuit serve when I do this modification? How do I analyze this? I already know this. I already know how this circuit behaves, right? I know the input-output characteristics of the D-flip-flop. So let me just write it here. T of t, Q of t plus 1, 0, 0, 1, 1. That's the characteristic table, the input-output characteristics of a D-flip-flop. I already know that. Okay. Now I want to analyze this new circuit, okay, where I have two inputs, two independent inputs. I can place whatever values I want on my J and K. This is not K, right? That's my K input. That's my J input. So these are the values, these are the pins available for me to work with. I can put any values I want on J and K. Okay. I don't know what Q and Q prime are because again, I have this feedback, the output of this circuit being fed back as an input to this circuit. So I need to know what those prior values were to be able to determine what this function is, f. Let me call that f here. And as you can see here, my f is nothing but d. If my f is being applied as an input to my d. So what is f here? If I want to write down the equation for f in terms of j and k and q prime, what would that be? My j or my f is nothing but d, right? My f is connected to d, so those are the exact same things. But what would that be equal to? J q prime, right? This is j q prime. This is an OR gate plus k prime. The other input here is q. So that's j q prime plus k prime q. Okay. All right. Now I would I would place my characteristic table this way. So that's my j because I have two inputs, j and k. What would that corresponds to d, which is equal to f, the same thing. And finally, what is qt plus 1? Okay. This is exactly the procedure we have been following so far, right? Every time we add on to an existing circuit whose input-output characteristics are known, I would basically use the modular approach to analyze the circuit. So exactly the same procedure I'm following here. All right, and then I will take different values for j and k because these are the values I can control. These are the pins available for me to put whatever values I want to put on those pins. These are the different values. Okay. Now, if I place j and k to be 0, 0, what is my d? If I place j to be 0, that becomes 0 plus k to be a 0, that means k prime is a 1, that becomes q, right? So that's 1 times q is q. In other words, I'm applying a value of q of t on my d, right? And in the next triggering instance, my qt plus 1 basically follows my q follows d, so that whatever I apply on d, that's what is mains, right? Which basically corresponds to memory. So with j equal to k equal to 0, I'm supplying back my q back to d. I'm feeding back my q back to d, so it's basically getting recirculated, but keeps that in memory. It does not change. So whatever value was there before, the same value gets carried on the next triggering instance. So the value of q does not change on the next triggering instance. What about 0, 1? J is 0, that goes, that basically makes it 0. K is 1, that means k prime is 0, that takes everything to 0. That means I'm applying a value of 0 on my d. So on the next triggering instance, my q follows d, so basically that becomes 0. That corresponds to the reset condition. So I can explicitly reset my flip-flop. Likewise, What about 1, 0? Placing J as 1, that means 1 times Q prime is Q prime, plus K as 1, that means K prime is 0, that's 0. Sorry, 1, 0, right? Sorry. K is 0, that means K prime is 1, that means that's Q. J is 1, that makes it Q prime. 1 times Q prime is Q prime. K is 0, that makes K prime to be 1, that means 1 times Q is Q. So Q prime plus Q, X plus X prime is always 1. On the next triggering instance, my Q follows D, so that's D. That's called the set condition. Okay. What about 1, 1? This looks very similar to your SR flip-flop, right? We have looked at the SR flip-flop. We had the set, we had the memory condition with S equal to R equal to 0, 0. We had the reset with S equal to 0, R equals 1. We had the set, S equals 1, R equal to 0. And we had the forbidden state with 1, 1. Let's see what we get here in this case when I have 1, 1 applied. So I'm applying J as a 1, that means 1 times Q is Q prime. K is 1, that means K prime is 0, that means that's 0. So what I'm applying on D? I'm applying a value of Q prime of D on D. That means in the next triggering instance, my Q T plus 1 becomes Q prime of T. Now this is something more very different from the forbidden state that we have seen before. Here the output is determinate. What that means is, if I had a 0 at Q at a point, applying J and K to be 1, 1s, on the next triggering instance, the output I know will be changing to a value of 1, right? Because whatever was before, in the next triggering instance, that value is basically being complemented. And it happens for every clock pulse. As long as I keep J and K to be 1, 1, I'm getting a complement of the previous value with every clock pulse. And this particular condition is called the toggle condition. Much more controlled, determinate, unlike the forbidden state. This is called a toggle state. Briefly, if I want to represent this in the form of a timing diagram, this is what it will look like. So these are my active edges here. With J equal to K equals 1 condition, I'm basically toggling my output. Let's say my Q was 0 to start with, so that's the next triggering instance, it was 0. On the next triggering instance, what happens? Qt plus 1 becomes the complement of the previous value, that becomes 1. It remains 1 until the next triggering instance. Now on the next triggering instance, again, the Qt plus 1 becomes the complement of this, that means it goes to 0. Complements goes to 0, complements goes to 0, and so on. So that's the waveform I would obtain. For the condition J equal to K equals 1, if I keep the condition to be constant, then my Q basically toggles with each clock pulse. Okay. That's the output I would obtain. So that's called the toggle state. Alright, so we'll stop here and we'll see in the next class how we can utilize the toggle state to our advantage. What can we build taking advantage of the toggle state. Okay, so with that, let me stop here and let me see if you have any questions before we conclude for the lecture. If you don't have any questions, then I'll see you guys on Thursday